Hello. Today we're going to be talking about OpenQAOA again. If you remember, or if you saw, there was previously a video I did on OpenQAOA um, back, I don't know, a couple months, maybe just 1 month. Time is an illusion, some amount of time ago. Um, that was basically some results from a closed beta that was being done. I believe I put it out as soon as the beta opened or something like that timeline. But anyway, I recently got wind that there was a more official release, bigger stability, lots of changes, a white paper, all that good stuff had come out. So I decided to revisit the software. So you can see right in front of me is the white paper. It came out just about a week ago. Um, and in this video, I'll be going over some more detailed examples of OpenQAOA code. I shouldn't say detailed, but more than the last video, I think. And some thoughts on the software overall. I've made some issues opened on the GitHub currently regarding some things. I might message they have a Discord as well and see about sharing these thoughts. Obviously, no one has asked for these thoughts, but I am deciding to give them anyway. So anyway, yeah, to get right into it, of course, the GitHub paper, documentation, everything, and code that I present today will all be linked below this video in the description. So the first thing that I want to talk about is the white paper. Here you can just see what the PDF looks like on archive. I always think it's, this is not related, but it's funny. People always say SDK all the time. For example, like Qiskit will say the Quantum Software Development SDK or something. It was actually, I had no idea what SDK was until extremely recently when I decided to Google it because I saw it one too many times. So maybe there's too much of an assumption there that somehow I've gotten this far in life and did not know it stood for Software Development Kit. I hope. Maybe I'm not even remembering it right. But anyway, you can see here that OpenQAOA is basically a set of techniques and implementations that sit above the backend and above the interactions with backend. So when I say that, you can think of OpenQAOA as sitting above Circ or Qiskit or any of those things. And so, and that's sort of shown there in figure 1. I don't really know anything about now that I'm actually looking at this figure, I don't know what sort of error mitigation, pulse axis, qubit routing stuff enabler. I don't know anything about the enabler. So now I'm actually going to go, okay, that is the only time it's referenced in the paper. I'm going to ask about that because I just noticed that, like, I don't remember anything about error mitigation or compilation, but maybe that's in the future as well. So as you can see, the white paper are very standard. The one thing I do, and this is just my preference, I think I'm not criticizing anything, but I do wish there was a little more background. I like my white papers, like the TensorFlow Quantum white paper, where that's like a textbook, right? You want to know everything about what's in the software. You don't need to go anywhere else but the white paper. Whereas, for example, RQAOA, which I'd heard of but was not extensively familiar with, like is given like a 1 sentence description here. Like, it would be nice to know more about that. Or Fourier, for example. Like, I know what a Fourier transform is, but I don't know what the Fourier initialization is. So just stuff like that. But that's just my personal preference. That's not like I know people who prefer quick and to the point. So you can see that this has information about QAOA. This is the software. Yeah, I'm really curious about the error mitigation. I'm actually going to I'm going to pause the video and ask about that right now. Okay, I did not get an immediate response, but I will probably post maybe in the comments of this video what the response. I guess the time in Singapore is just not optimal, which is fine because it's very different time there. So anyway, getting into it, let's see, yep, sharing. Basically, let's just go over to workflow. First of all, I encourage you to check out the first video. Although the software is different, a lot of things are similar. So basically you define this is the workflow. You say, you initialize your QAOA. It's very object oriented, which is interesting. You compile it for a given problem, and then you optimize it, and that's it. This is the minimum, MVP right here. But there's a lot of stuff that goes into this. For example, here you have the preparations. You have your problem defined here. You have cost Hamiltonian that comes from that. You can define a mixer. Layer is the parameterization type. Warm starting, parameter initialization. I don't know. We're going to be talking about warm starting. I did not know it was built in though. And then the typical optimization and results. You can see here that the parameter type is normal, random initialization. This is the backend basically that they're using, which is a Qiskit simulator. And this is why I said it's sort of on top of it, is because it's using tooling and circuits from Qiskit and other just different things like this. I don't know what CVAR alpha is for if you're using Nelder-Mead. I don't know what that's going on in there, but yeah, that's it. Nelder-Mead is the optimizer that is most frequently used. And then you can change the circuit types. You can run it on real hardware, which would probably be very expensive to run anything on scale on any back end of reality. We have the results, and that's pretty much the workflow. You can see more advanced example here where you specify specific sort of functional forms. Yeah, so let's just get into the code and documentation real quick. First, I'll just go over to this is the GitHub page right here. Nice GitHub. And this is the documentation. And this is my key sort of, I don't want to say complaint, but I think this is the biggest thing that could be improved, is that when I was making this code, that I'm about to go to, right? So I used this software a couple months ago. I admittedly have not done much with it since then. So I have some knowledge. I'm jumping in. I'm saying, how do I do this stuff? I have plenty of QAOA knowledge. I have plenty of Qiskit, Circ, etc. experience. So how do I use this? And there was a lot of times where I felt sort of like a clash, like I was grading against some of the software, especially when it came to the documentation. And that's partly my fault. I don't want to blame, like I'm not blaming people. Like this is a thing that I have where I am trying to do things that maybe the software is simply not built to do. For example, one of the first things I was trying to do is use other mixer Hamiltonians. And it says right here it supports X and XY. I think there should be support for custom mixers. I always like giving custom options, even if they're rarely used, but I did not see that anywhere how to do custom. I don't think it's currently supported. So that's just an example of maybe I should make a feature request. Let me make a note actually to do that, and I'll do feature request for custom mixer. There, I will do that. But just things like that. And then when it came to documentation, I'll just get it out of the way first. I'm gonna say good things later, I promise. And this isn't bad. I'm not saying this is bad. I'm just saying this could be improved. For example, this is something I did just make an issue of. When I was going to the results, I was like, okay, I have this results object. I don't know any of the attributes. I don't know how to get anything from it. And there's nothing here. It's just, there's no documentation in the logger or result. Another thing will be, and here I'll just bring up a tutorial, right? So the tutorials are really good. I'll say that. And I think they're pretty good. But the thing I was going to say is that, for example, suppose you want to do SPSA, right? That's it's supported if you go to optimizers, somewhere. There we go. If I go to optimizers, I'm like, I want to do SPSA. That's really common. Minimize fun, set method equal to SPSA. Lots of functions that I don't care about. I'll just accept the defaults. So I change method to SPSA. It breaks. It breaks immediately. You can't do that because what happens is you have to specify. Let me go over to see exactly what this is called. You have to specify a jack or a Jacobian JAC, saying grad SPSA as a string. That's inside a class of classical optimizers, which has a lot of valuable information that I don't see in the documentation. There's constraints in there even, there's bounds. Like, I don't know. I was able to figure this out because I went to the source code and looked at the doc strings inside of this class, but I didn't see that in the documentation. Like, you think it would be in like the optimizer section, but it's just not there. So by the way, if you want to use any derivative based optimizer, you have to specify a Jacobian function. Also, it doesn't have adjoint differentiation, which is fine. I just that's like, doesn't really matter if you're trying to do real hardware, which is exactly what they're trying to do. It's just something that when I was doing this, I was like, oh my god, I did not realize how slow the parameter shift simulation was. I'm so used to, doing adjoint, getting things instantly. It was a quick reality check right there. But anyway, yeah, that's pretty much the main sort of thing. And then, for example, I'll give another example of where I think documentation could be improved. When I go over to the workflows, so I go to QAOA. So I have this, or I'll just go here. So I have this initialization, right? Init type rand. So then I set it to custom, which one it would be nice to see. You can see here circuit properties. This is like not rendering correctly, I believe. So I can't even see all the options, whereas these have nice options right here. I actually, of course, I'm saying there's no classical optimizer. It's right here. It would be nice to say that this is required though. You can see it says like there's no optional here, but obviously all of these are optional. They're not supplied. And so just saying this is required for gradient-based optimization. I also think this would be better put, I don't know, maybe I'm just confused about the whole workflow in terms of like, some of it's very functional and some of it's very object-oriented. But anyway, you should ignore my complaints in all reality, because they're probably just because I did not spend enough time with this software and I want things to work for me instantly, doing exactly what I want to do. So that's the worst user you could possibly have. But anyway, you can see here that like, if I want to put the initialization as custom, what else do I have to do? How does this work? Where do I put them in? Turns out it's called variational params dict, which kind of makes sense, but it might make more sense to be like initial parameters dict or something like that. But then what are the arguments of the dictionary supposed to be? I don't know. It doesn't tell me that. So if you actually go to the code, you can see examples, and you can see examples in here as well. If you go through all of them, I believe the OpenQAOA landscape might have it. I don't know, maybe not. But basically, just bringing that to the forefront of saying, how do you do everything and what's actually required too. The tutorials are great, but a lot of them are small variations on things. For example, I don't remember seeing one that used a gradient-based optimizer, but that's just, maybe there is one, I just missed it. So just stuff like that. Also, this is not helpful, the value of the CVAR parameter. I don't know what CVAR is, and there's no search for Google. Like if I go to CVAR, conditional risk investment, like, see, this is an example right here of where I think more making it so I don't have to leave your white paper, making it so I don't have to leave your documentation for any reason, is I think good. Obviously people disagree with me, but like, I don't know what that is. I still don't after looking it up. And then, yeah, so that's the main sort of things. It's just I think there's little things like that that can help make the documentation cleaner. I think a lot of the focus though is on interacting with backends, which I did not do because I did not want to pay $1 billion to use real backends. So yeah, let's actually get into the code now. I feel like I've been too rude. I don't mean to be rude. I'm just saying like I think there's room for documentation improvements. And you're welcome to disagree with me. Because I probably am not the most targeted user since I do not do QAOA on a daily basis or like on real hardware. So anyway, hopefully now, now that we're getting into it, this will actually be useful for people trying to learn about the software. So what we're going to be talking about is two things: parameter concentration and warm starting. I will link the parameter concentration paper below, of course, which basically says for certain values of P, the parameters gamma and beta concentrate towards certain values. I was not able to replicate this result, but I'll explain why shortly. So the first thing we're going to be doing is working, of course, with maxcut for QAOA. We import the problem maximum cut, and it'll do everything for us. We also create a device that's sort of like a Q node, and penny lane is how I think of it. And then we from optimize, and this is kind of weird too, from workflows optimizer import QAOA and RQAOA, and my understanding are like the two like big things, like everything comes from them or is a class method of them. So it seems like that should be higher up, but I don't know. These are the functions that the parameters are supposedly going to concentrate around. I did not find that they actually did that, but I just took these values from the paper. So what we do here, you can see that we create a random instance of our maximum cut problem. We specify the number of nodes, which is, we're varying here, edge probability, and then we want to get the actual quadratic unconstrained binary optimization problem. From that, we create our QAOA, we create our device, which is just the default backend. Basically, they say it's a lot faster in one of these tutorials. It's a nice graph down here. Wow, so much faster. I don't know how much to believe that or not, but I'll take it at face value and say, okay, it's super fast. So let's use super fast things. We set the device to be this thing. We set our circuit properties. We want P equals 1 because that's the parameter concentration we're evaluating. Normal parameters, random initialization, and standard X mixer. There's no fancy states we're prepending or appending. And the optimizer here, we're doing RMS prop, just, I don't know, the closest thing to atom. And parameter shift differentiation, of course. Maximum iters 200. We keep track of the progress. We compile our QAOA around this problem, which will create, of course, the cost Hamiltonian, and then we optimize it. We get our results, and we get the angles here. And this is an example, right, where I'm like, how did I know that results.optimize key value optimized angles is actually what I care about? And that's because I went through the code, and maybe it's somewhere. Once again, I want to say it's possible that the documentation is there. It's just not as easy to find as I would like it. Then we repeat for a certain number of times, and then we get our results. So you can see we already went through and did this. And you can see that this is supposedly how the trend line is supposed to go from the paper. I did not see this. You can see it does not really look like they're following that trend. But I believe this is because I'm not actually, if you actually look at the energy differences, these are not converging to the optima for whatever reason. Not a software reason, it's just, representation or something like that. And so I think there's just problems in the optimization. Maybe if I chose a different optimizer, this would look good. And so I won't dwell on this too much. My goal wasn't really to recreate this paper, but to use this as an example of the OpenQAOA workflow. And then for this one, we're going to be looking at warm starting. So what is warm starting? Warm starting is basically you take the parameters from a smaller, or I shouldn't say, in this case, I'm taking them from a smaller problem. Warm starting in general is just starting with a specified set of parameters that have some potentially favorable attributes. There's lots of ways you can warm start QAOA. In this specific example, we're going to be warm starting the problem based on the solution to a much smaller problem. So we're going to be looking at the variations in depth and width, so p and qubits. So the first thing we're going to do, right, this is the number of p-values we're looking at, this is the qubits we're looking at. We're going to first solve our small problem. So this is a simple, just a random max cut problem with 5 nodes. This is a 5-qubit problem with depth 1, so very small, very easy to solve. We get a solution. We're then going to go through for these p's and say, okay, using those values, once again, 5 nodes, but completely different problems. So different problems. We're going to go through and we're going to warm start it by using those parameters as our initialization. So you can see here I define the betas, because remember, as p increases, there's more betas, as this initializations here, and the gammas as the initializations from this warm start problem. You could even do more work by warm starting from the previous depth, but that's less realistic. So what we're just looking at here is warm starting from the smallest problem. And we can see we're going to be plotting the results compared to random initialization. So when we do that, we can see for a variety of p what's going on. Here's an example where warm starting in the long run is actually not beneficial. You can see there's an initial benefit, but in the long run, cold starting works out better. Here's a contrary example where warm starting does do better, and this is more common. You'll see it's able to start much lower and converge faster. Here's another example. They actually both converge to pretty much the same spot. But this is a great example where it just is warm starting is continuously better. They basically converge to the same. Warm starting is much better. Warm starting is about the same. Warm starting is better. So what I'm trying to say here, and this was actually surprising to me, I'd done very little work with warm starting, but this is basically free gains. I mean, even if you scale this up to and we'll talk about qubits later, but even if you're like, okay, I can't simulate, I scale this up to some hardware problem, like I can run my 5-qubit system here, I want to scale this up to max cut on 400 qubits, right? Even if I use this, now, maybe it wouldn't scale that well. Well, I'd be interested in knowing, but there's, zero cost, basically. The cost to simulate a 5-qubit system is nothing. And so there's benefits that you can get for free, which is really cool. And I never really looked into before, but like that's lots of good benefits for literally free that you're getting. Now we're going to do the same thing, but change the size. Once again, random and different problems for every example. But this time we're increasing the size, but we're keeping p equal 1. And so we can see these are smaller problems. This is 3. We trained originally on 5. So you can see it converges much faster. 4, that's a big difference, right? It converges right away, but this takes forever. 5, this is actually, we trained originally for 200, so this would probably get to the same in about 200 iterations, but you can see, look at that, instantly ready. Big difference, but of course that's not surprising. This is the same basic problem we trained on. Here's a good example. 6 gets hard. I guess this one's just hard to train. They're both in local minima, but this is just a better one. Here's another example. 7 is hard to train, but warm starting is good. 8, you can see as we scale in qubits, the advantage of warm starting is much more apparent. And this is really surprising to me, just in how easy it is to get better results. I'd be interested to see, well beyond the 10-qubit barrier, what exactly that would look like. But basically, you can see the same setup we're doing here, and this is why I said it wasn't super detailed. Is because we're using a very vanilla workflow. There is some advanced, for example, the Jacobian and the initial parameters that is sort of more advanced, but pretty basic as far as it goes. So the last thing I'm going to say is, of course, everything I said will be available below. Um, the last thing I want to say is that I know I started off with some complaints, but I think overall there's a lot of potential to the software. There's a lot of advantages to getting in early or using things early on software. Um, and I'm sure things will change in the future, but the GitHub and Discord servers are very responsive and active, which is um, essential really to building software. You need to build a community, and so like there's so many, right? There's a billion quantum software things out there. So how are you going to choose which one to use? Well, it's probably going to be easiest to use, and easiest to use is often easiest to debug, which means it's easiest to ask someone about in most cases. And so that's why community building is so important. And so I think they're taking great strides in that direction. I think there is work to be done to improve the documentation, and I would like to see more features added. But I think there's lots of interesting work going on. I encourage you to, if this software looks interesting to you, try it out, see what's going on, run it on real backends. That seems to be the real purpose, right? Is to be, as you saw, or maybe you didn't see in the paper, but want to scale it up to hundreds of qubits. Well, we have more than 100 qubit systems, so try running on them and find out. I did not do that, and I will probably not do that simply due to my limited access, but I encourage you to. So once again, I want to say, yeah, hope you enjoyed it. Everything will be below, and cool software, still work to be done. And just in case anyone's wondering too, since I made 2 videos on a relatively niche software, like everything else I talk about is TensorFlow Quantum or occasionally Penny Lane. No, I am not being sponsored to produce this content. That would be nice to get sponsored to make videos. But I am just doing this because I saw that this, I was in the beta originally and I saw this come up again with the white paper, so I figured I'd revisit it. But I figured I'd say that because I always wonder sometimes when people are doing this stuff, like, is someone paying them to say this? Don't worry, no one is paying them to say this. I am just doing this for free. So yeah, check it out if it looks interesting, and if it doesn't, then don't.